I will talk about joint work that I'm presently doing with Giovanni Valenta, who is, as we all know, here, but has a fever and cannot come. We'll hear later from Patricia how he is doing. So I will sort of take the opportunity to present this joint work, and I should say that much of it is still premature and just tentative, but I nevertheless hope that it will be interesting to you. So can I go to the next slide, or how do I do that? Should I use these? Okay. Yeah, this one. So here's a sort of overview of what I intend to do. I'm not sure if I can all fit it within the framework that in the time that is allotted to me, but I will try to draw a comparison between the classical Boltzmann equation that we all know and love, and a quantum version of that, ordinarily called the quantum Boltzmann equation, which is used quite extensively, especially in areas like solid state physics or condensed matter theory. And in both cases, I will focus on the question of how and whether you see an emergence of irreversibility in those equations. Because that's what the Boltzmann equation is most famous for, at least in philosophical issues, that it sort of shows, I mean, for many people, it shows a sort of, at least in principle, it is possible to start out from a mechanical theory, whether it's classical mechanics or quantum mechanics, theories which are famously invariant under time reversal and would not necessarily distinguish the past and the future direction of time. And from that theory, still derive a result which is not time reversal invariant, namely a tendency for systems to move in the direction of equilibrium and not away from equilibrium. And certainly this was also Boltzmann's claim to fame. He stressed the aspect that his Boltzmann equation implied such a result very strongly, and he claimed he had derived the second law of thermodynamics from his considerations. I will investigate this claim and if what are the ingredients to draw such a conclusion in both cases and try to compare those two. So I will do that in a little bit of a historical fashion. I will first go into the classical Boltzmann equation and show how Boltzmann argued in that case. I also want to go into the way in which his approach has been taken over in the later textbook literature, because what people have been learning in the 20th century about the Boltzmann equation is in crucial ways different from the way in which Boltzmann himself approached the matter. And I will show you that, or at least I will argue, that a similar distinction is also apparent in the quantum case. So there are strong connections or strong similarities between what happened in the classical theory and what's happened in the quantum treatment of the Boltzmann equation. So here is more or less how I will proceed. I will start with reminding you of the classical Boltzmann equation and how irreversibility seems to enter there. I will then go into how this has later been picked up by the literature, especially in later textbooks. Then I will give you a sort of heuristic argument for why a Boltzmann-like equation is relevant in condensed matter theory. And then I will show you, I will take one approach of David Snoke to derive that Boltzmann equation and see what the crucial ingredients are that he relies on. I'll also show, briefly discuss how this is done in other approaches. And then I will try to formulate a conclusion about how or whether you will have a derivation of irreversible behavior in the quantum Boltzmann equation. So, to start off, well, I told you what the aim of the talk is, so I won't repeat that. But I do want to say a little bit about why I take this historical approach. And the reason for that is that I think it's important to learn history to see what mistakes people have made. Because if you don't learn that, you're very likely to commit the same mistakes again. So that's one reason why it's still relevant to look at these historical works, even if we can still say, well, we don't have to completely follow these ancient or classical authors. We have our own modern day understanding of these things. So here is Boltzmann's derivation of the Boltzmann equation. He did that in a paper of 1872. He had been working on similar issues in what we today call the kinetic theory of gases from 1866 onwards, with mixed results. But in 1872, he writes this very important paper, and he takes a completely new approach to the subject, which he borrows from Maxwell. Maxwell had been studying kinetic theory of gases in 1860 and more importantly in 1866. And somehow in the late 1860s, Boltzmann became aware of those papers. And what's more, he discovered they were written in an unknown language to him. So he had to learn English in order to be able to read Maxwell's paper. And when he finally did that, he became very enthusiastic about Maxwell's approach and wanted to extend that approach to new directions. So that's what he tried to do. And while Maxwell had considered himself only with the question of characterizing an equilibrium state for a gas consisting of molecules, Boltzmann wants to set up an evolution equation for how such a system changes in the course of time if it was not in equilibrium. And to do so, well, he makes a few modeling assumptions. He considers what we now effectively would say is a hard sphere gas consisting of spherical molecules, a finite number of them, and see if I can put it. So the n spheres, each with a given diameter a and a mass m, and they're all contained in a vessel of volume V. He characterizes that gas by a distribution function. He makes also a simplifying assumption in the first part of his paper that the gas is spatially homogeneously distributed. So the only parameter that you have to consider for the molecules are their momenta. So there's a distribution over the individual momenta of the particles. He represents that distribution by a continuous function f. And the meaning of this function, roughly speaking, is that if you take this over a small interval of the momenta values, then this function will give you the relative number of particles that have a momentum within that interval. Now, as has been remarked yesterday when Charlotte gave her talk, the question is really how can you say that the relative number of particles, when there's only a finite number of them, can be represented by a continuous function? Is it an approximation? Is he using some smearing function to construct this continuous function? Boltzmann is completely silent about these issues, and presumably he thought, I mean, he is just taking over this idea from Maxwell. So Maxwell had not been criticized for this approach. Boltzmann, therefore, also didn't have any reasons to doubt it or to suggest that this was controversial. He just takes Maxwell's construction over and goes with it. So the question is really how that function, this distribution function, will change in the course of time. And the mechanism for change is really the collision of particles. So they can only collide elastically. And of course, if the gas is dense, then there might be multiple collisions going on simultaneously. But he assumes that the gas is so dilute that we only have to consider binary collisions between pairs of particles. And an important assumption that I will mention later is going to be the Stokes-Thal set. But first we have to consider a little bit the collision process by itself. It can be characterized as quite abstractly as a process in which two particles with initial momenta collide, and then these initial momenta are transformed into final momenta. And the ordinary laws of collision, of elastic collision in mechanics, are such that the final momenta, the primed variables here of particle 1 and 2, are functions of the initial momenta plus a vector omega that is the vector that points from the center of particle 1 to the center of particle 2 at the time of collision. So these are the only parameters you need to know in order to be able to calculate what the final momenta are in terms of these initial momenta and the vector omega. Now this transition T has nice properties. It's an involution, so it's equal to its own inverse. These are very nice properties. But there's one important thing that I need to mention in my interpretation of this as a process in which these are the final momenta and P1 and P2 are the initial momenta. And that is only true if there is a certain condition on omega. the inner product between omega and the difference between the relative in the relative momenta has to be positive. If it's negative, then it's still a collision, but the incoming momenta are the primed variables, and the outgoing momenta, the final momenta, are the unprimed variables. To see that, I have these two schemes over here. Here you see particle 1, the red one, and particle 2 is the blue one. This is the vector omega. I didn't have the omega form, so there's a W here. With omega 1, 2 is points from the center of particle 1 to the center of particle 2. And it's multiplied by A, which is the diameter of a single molecule, and it's also the distance between the center of the two. And as you can easily see, I hope, is that this is P1. If you subtract P2, and you get a vector like this, and the inner product of that vector is positive with omega. So this is indeed a collision in which P1 and P2 are the initial momenta, and P2 prime and P1 prime are the relative final momenta. If the vector points in the other direction, if this is particle 1 and this is particle 2, so still the red one is particle 1, the blue one is particle 2, then we have a similar collision with the same 4 parameters. But here, the particles with P1 and P2 are moving away from each other, not towards each other, as in the first. And so they are the final momenta after the collision with initial momenta, P1 prime and P2 prime. So regardless of the direction of omega, we are talking about a collision. But if the inner product is positive, it's a collision between initial momenta, P1 and P2. And in the other case, it's a collision with the initial momenta, P1 prime and P2 prime. I hope this is clear, because this is important to understand what follows. And as I heard from Charlotte, it's easy to be confused about this issue. Many people were. But here is how the situation goes as follows. If we want to consider the rate of change of this distribution function, say for some value of momentum P1 in a given range delta P1, then we have to consider all the collisions in which a given value of the momentum could change. And so we need to know the relative number of pairs of particles which have the momenta P1 and P2. And as I said, there are two kinds of collisions here. If the inner product of omega and the difference of P1 and P2 is positive, then we have collisions in which P1 and P2 are the initial momenta and primed variables are the final momenta. If the inner product is negative, it's the other way around. In the first type of collision, we see that that leads to a decrease of the number of particles with P1, because we had an initial value of P1 that is transformed into another value by the collision. So that leads to a decrease of the number of molecules with P1. If the other type of collision occurs, then particles who had different momenta from P1, one of them changes into a final particle with P1. So that leads to an increase of the number of particles with P1. And so we have to consider both of them, and we actually have to draw up a balance. We can simplify this integral that I wrote here in equation 2 into one in which I only consider the so-called incoming representation, only consider the case in which omega, this inner product is positive. But then I have to make a subtraction. So these are the case in which P1 increases, in which case these two are the initial momenta, and a minus sign for the decrease of the number of particles in which these two are the initial momenta. And then integrate over all values of omega and all values of P2. So we're halfway there, but we still need to make an assumption about these numbers of pairs. And that is the famous Stootstaal-ansatz, the assumption about the number of particles that collide. Boltzmann assumes that at all times, the relative number of particles that collide is proportional to the product of the relative numbers of their respective initial momenta. So for one of the terms of the integral I had, this one, in which case these two are the initial momenta, we can write that as a product of the respective one particle distributions. For the other type of collision, it's the primed variables that are the initial momenta. And so we must write that as a product of the primed variables. So if we now put these considerations together, we can substitute these products in the equation we had on the previous slide, and that is the Boltzmann equation. Because the result of all these manipulations is that I now have an equation that tells you what the rate of change of a single particle distribution is going to be in terms of that single particle distribution for other values of the momentum. But there are no other functions concerned. So it's an autonomous equation. It's a difficult equation. It's a nonlinear differential integral equation. But at least you can meaningfully ask what its solutions are. Now, I have to emphasize that this Stootstaal-ansatz is peculiar. It's not just an assumption about an initial state. It's an assumption you have to make for every collision that occurs in the history of the gas. For each of those collisions, you have to assume that the incoming momenta prior to that collision are independent, while the outgoing momenta might not be. So you have to evoke that again and again and again for each collision in the history of gas. But it leads to the important virtue that we now have a autonomous equation that governs the rate of change of this distribution. It's a difficult equation, so the results about the solutions or the possible solutions of these equations are still very limited today. But foregoing the problem of solving this equation, Boltzmann was able to show that if this equation holds for all times, you can derive an important result. And that is that if you introduce this particular functional of the Boltzmann, of the distribution function, known as the H function at the time, you can show that that function has the property that it can only decrease in the course of time, monotonically in the course of time. And that implies irreversible behavior. It shows you that in a sense, the evolution of that distribution can only proceed in one direction only. And as Boltzmann showed, it's the direction of going towards equilibrium, not going away from equilibrium. Boltzmann also showed that if you take the distribution to be the function, the form of Maxwell's distribution, then that is stationary in time. And he sort of assumes that necessarily, since this can only decrease in time, it will also decrease until it reaches the Maxwell distribution. That, of course, doesn't quite follow from his arguments, but I'll forgive him for that omission. The important thing is you've got a result that is asymmetric in time. And Boltzmann, as I said, stressed the necessity of his conclusion and the important generality of it, and said that he had succeeded in deriving the second law of thermodynamics, in which he identified or interpreted H as minus the entropy of the system. So the decrease of H will correspond to an increase of entropy. Now, if you ask yourself, where does that asymmetry come from in a theory that is otherwise completely invariant on the time reversal? The answer, I think, is simple. It comes from the Stokes-Cell ansatz, because that is an assumption which distinguishes between the initial and the final values of the momenta. If you were to reverse the direction of time, then the initial momenta become the final momenta, the final momenta become the initial momenta, and you can easily see that that would lead to another equation, the so-called anti-Boltzmann equation, which differs from the Boltzmann equation by a minus sign in the right-hand side. And that would lead to an anti-H theorem in which H can only increase rather than decrease. So it's definitely true that this Stokes-Cell ansatz is an assumption that breaks the time reversal invariance in theory. And that is responsible for how you could get a irreversible result in the first place. Nevertheless, Boltzmann himself didn't put any stress on the importance of this assumption. As a matter of fact, he writes the following about this issue. He says, the determination of the number of collisions, the Stokes-Cell, can only be obtained in a truly tedious manner. But since this determination has, apart from its tediousness, not the slightest difficulty, nor any special interest. And because the result is so simple that one might almost say it's self-evident, I will only state the result. Now, he doesn't do that, he gives a derivation. But the fact that he emphasized here that the result was without any special interest and was actually only very simple to the point of almost being self-evident, certainly did not alert his readers that this was the passage where the most essential ingredient is being introduced. And so one of the questions that historians have asked is why was Boltzmann so cavalier about his Stossel? And I agree with what Darrigal has mentioned in this point, is that he did not realize at the time that this was a crucial point. As a matter of fact, he did assume that the Stossel ansatz was natural and almost self-evident and didn't need any further argumentation. Presumably because Maxwell had used the same argument. But Maxwell had also assumed that the number of collisions between a pair of particles is proportional to the number of particles that have initial momenta P1 and the number of particles with initial momenta P2. And since that was his most direct inspiration, Boltzmann was probably, it was natural for Boltzmann to assume that this was something that was uncontroversial and almost self-evident. And of course, in Maxwell's case, it doesn't matter much because Maxwell is only considering equilibrium distributions in the first place. But if you want to describe, as Boltzmann is doing, whether systems approach to equilibrium or whether they move away from equilibrium, then it becomes a very different issue. Nevertheless, a few years later, it was Boltzmann's friend Joseph Loschmidt who first pointed out to him a possible objection. And Loschmidt said or wrote that he has to be careful with these type of arguments because mechanics is time reversal invariant. And if you therefore allow one type of evolution, then the time reversal of that evolution must also be a possible one. And if one evolution leads towards equilibrium, then the reversed evolution will lead you away from equilibrium. And you can't have a theorem that allows one and excludes the other. Now, in his response to Loschmidt, the way he argues is rather complicated, and I won't try to summarize it here. But the result in his own work was that it led him into developing a completely different approach, the so-called combinatorial argument, which is now often called the Boltzmannian approach. And whatever you can say about that, the question about whether or what motivated the Stossel ansatz in his previous work is not further clarified here. Nevertheless, I want to remark that Boltzmann's 1872 paper was very well received in the physics community. And in fact, in 1888, early that year, he was invited by the university in Berlin to become the successor of Gustav Kirchhoff, who incidentally had been the very first professor in the world who had an appointment in theoretical physics. And they wanted a successor that was also a theoretical physicist. And the search committee identified 3 possible candidates for that position. Number 1, Ludwig Boltzmann. Number 2, Max Planck. Number 3, Heinrich Hertz. So they invited Boltzmann, and Boltzmann accepted the professorship in Berlin, which was that was the center of science and physics in the world at the time. So this was a very prestigious position. And connected to his accepting the professorship in Berlin, he was also elected as an extra perk to the Prussian Academy of Sciences. And that academy wrote a report on his candidacy in which they wrote, Maxwell's work has proved that the distribution law for the various values of the velocities between the atoms in a gas, which Maxwell only verified as a correctly guessed hypothesis, must necessarily be of the form of the final state, that is the equilibrium state, that Maxwell had guessed, through the collisions of the molecules. So they stress that this mechanism of colliding molecules will necessarily lead to the equilibrium state of Maxwell, the final state. In this work, he has shown the high degree of abstractive power and the skill to overcome extremely difficult and complex problems. Signed by Helmholtz, Kronecker, Petzold, and Siemens. So this shows you that how his work was received at the time. And one of the reasons for why I want to point out this particular episode is that there is a current belief, impression at least, especially due to Boltzmann's own writing, that he was somehow completely neglected in the scientific world. When he's later criticized, later criticized by Zermelo, he thanks Zermelo in a sort of sarcastic manner for his criticism, because he said, I'm still thankful to Zermelo because this is the first time that my work has been noticed at all in Germany. When he had been invited to become professor, the most prestigious professor in theoretical physics in Germany a few years earlier. So you shouldn't always believe Boltzmann on his words. Of course, the professorship didn't materialize, but that is a different issue. You can ask me later if we have time. Still, this problem about how can we have an irreversible result derived from a theory that is patently time reversal invariant still simmered on below the surface, and it emerged specifically in a series of papers that were published in Nature in 1894 after famously Dolfrewell had asked the question, can somebody say what the H theorem actually proved? And there are about a dozen or more authors who jump into that debate, and let me roughly characterize that debate as a comedy of errors. You see all kinds of opinions being put forward. There's a lot of confusion um, and unclarities in this debate, but I can say one thing, and that is that Burberry's contribution to the debate is that at least he pointed out that Boltzmann had made an additional assumption that broke the time reversal invariance. Now, Burberry's own formulation of that assumption, which he called assumption A, is not very clear, and I will omit going into details here. On the other hand, Brian, who also jumped into debate, clearly pinpointed the Stoßal ansatz. But instead of arguing that that was a additional assumption, which was not motivated by the mechanical theory itself, he argued that this was a completely natural assumption, and that in order to make the inverse assumption, that the final momenta were uncorrelated, you would have to attribute foresight to the molecules. And that this, since that was unnatural, the Stoßal ansatz was therefore almost self-evident. Now, when Boltzmann also jumped into that debate, and shortly afterwards, he wrote his 2 volumes on the lectures of gas theory, he credited Burberry's paper in which, and said, yes, indeed, my theory involves an additional assumption. And this time he invented a new name for it. He called it molecular disorder or molecular chaos, depending on how you translate the German. Unfortunately, Boltzmann in this book is not very precise about what that condition or assumption means. He says only that he gives a few examples, and he describes the condition as saying that there are no special correlations amongst the particles in the gas. In the end of his discussion, he says that, well, the condition of molecular chaos could be defined simply by the demand that Maxwell's collision formula holds. So you could ask, what does he mean by Maxwell's collision formula? Well, my interpretation is that he refers to the Stoßal ansatz, because that was used by Maxwell in the description of collisions, and Boltzmann had taken that over. But perhaps there are other interpretations of what he means here. So it's not very clear in how he understands this condition of molecular disorder. Nevertheless, later on in the next century, there is a tradition of textbooks that discuss the Boltzmann equation. And the first of those that I was able to trace is a book by James Eugene, 1902. And he states this condition of molecular chaos, and he tries to formulate it, and he does it in a way which is very different from what Boltzmann had said. And there's a whole tradition of textbooks here. I've written a few authors. So there's Huang, there's Lanford, of course, there's Sergiani and his co-workers, who all adopt a certain assumption, which they either call molecular chaos or molecular disorder, or sometimes call the Stoßal ansatz, implying that the two are equivalent. But the way they formulate it is roughly as follows. And I'm taking Huang as an example here because he is the most explicit and also comes to explicitly recognize that he got himself in trouble. So what is the assumption of molecular chaos that they use? The assumption of molecular chaos, according to Wang, states that in the spatial volume element dq, the number of pairs of molecules with respective momenta lying in momentum elements, that goes in one direction. The number of pairs of molecules with respective momenta in two elements is proportional to the product. So yes, this is an assumption about independence of the molecules. But Wang doesn't mention collisions. He doesn't mention the distinction between the initial and the final momenta in a collision. He just talks about pairs of molecules. And sure, if you make this assumption, it's possible to derive a Boltzmann equation. If you make this assumption at the initial time t0, it's possible to derive a Boltzmann equation for positive time. But if you then ask what happens at earlier times, you will notice that this assumption makes no distinction between the order of time. It doesn't refer to earlier or later in any way. It's time reversal invariant. If you change the momenta into their negative momenta, the equation still holds. And so this is time reversal invariant. So it cannot possibly play the role of the Stokes hypothesis. And Wang realizes this later in his book because he sees then that if you go back to negative times, the system will move away, seem to be moving away from equilibrium to reach this distribution at time 0. So there are two consequences of this assumption, and that is that you will have a decrease in the H function for positive times, but there is an increase in the H function for negative times. And if you take the two together, then at time t0, you will find that the H function doesn't change at all, which would mean that we are already in equilibrium. And so the only solutions that are allowed by this approach are the equilibrium solutions, in which nothing changes. And that is a very meager understanding of a derivation, the Boltzmann equation. It doesn't imply any irreversibility. And mistakes similar to this are committed by all the authors that I mentioned above. So it's curious to ask, how could this whole tradition of textbooks all take the same approach in which they replace what Boltzmann explicitly understood as a time asymmetric assumption and replace it by something else that is time reversal invariant? And how can they still think that they're deriving the appearance of irreversible behavior in physical systems? I can only speculate about how that came about, but of course I have to admit that Boltzmann's formulation of the social answer was mathematically very obstreperous. As I told you before, it would have to hold at all times. For each collision, again, you have to assume that the initial momenta are independent. So it's very hard to use in a mathematically concise derivation. On the other hand, if you take that factorization condition that Wang formulated, or genes before him, it's mathematically rather simple to derive a Boltzmann equation for positive times. And if you forget that there also might be negative times, and you only focus on the positive times, you will say, oh, I'm done. And it's easy to stop there. And I think that is so, yeah.
I assume factorized condition holds at a certain time, then I get the right formula for df or df at that time. But if I want to say that some positive time after that, I have the same formula for df over d, I need to assume factorization or social something at that later time too, right? Because the factorization holds at one time, as for the equations, it's not necessarily going to hold at later. Yes.
I'm not quite sure. You might be right. Yeah. Yeah, but that's not what I'm doing here.
No, I mean in terms of what you say you find the bunch ways, if you derive it BBGTY style, then you're truncating at the 2-point function, and then you're imposing in addition an assumption of the 2-point function being uncorrelated at an initial time.
Yeah.
And at that point, at least of the perturbative accuracy of the truncation, you don't need to keep reimposing it. The one-off imposition suffices.
Yeah.
We wonder if it limited the amount of time for which that accuracy would be.
I'm not sure.
That is the most important difficulty in the derivation. These textbooks usually do not go in greater detail. Of course, Lanford is an exception here. Anyway, I can only say that there must be some attraction in following this approach and forgetting the problem that it could also be applied for negative times and then leads to completely different results. So this is what I wanted to say about the classical Boltzmann equation. And I want to go over to the quantum case. Can I ask how much time I still have?
It's been almost an hour.
It's been almost an hour. Oh, so I have to be quick. First of all, I wanted to give some heuristics for how or why a Boltzmann-like equation might be relevant to areas like condensed matter theory. Because on first sight, I was surprised when I first heard there was a quantum Boltzmann equation. I thought, how can this be? I mean, Boltzmann's equation concerns very dilute gases or classical particles. In condensed matter, we're considering condensed matter, not dilute matter. And typically we are using quantum mechanical systems here. Well, here's a way to understand how a Boltzmann equation can still be relevant in such situations. And the easiest way to introduce that is to consider a system of fermions, like helium-3 atoms And for the moment, at least, ignore any interaction. If you have a system like that, and you ask, what would it look like at temperature absolute zero? Then it must be in its ground state, and its ground state for fermions is something that which you fill up all the lowest levels up to the so-called Fermi level, because the Pauli exclusion principle will permit only 2 particles per level. If you have n particles in your gas or in your system, then you have to fill up all these lowest levels until you reach certain threshold. So this is what the system with all these what these energy levels look like. If it's non-interaction, then the energy is all kinetic energy. So kinetic energy is proportional to the square of momenta. So they fill up a ball in momentum space, and all these different levels are indicated here. And all the particles with up to energy, which is given to by the Fermi level, are filled in this ground state. Now I ask myself, what happens if I give a little bit of energy to that system? So I raise the temperature to a very low value, but above absolute zero. Then you will expect that there are some particles that move to higher levels. And they will leave a hole below the Fermi level, which is indicated here. There's one particle missing here, it's a hole. And there's one particle in a higher level, that's an excitation. So there will be a few of those. And although the entire system is very condensed, most of those particles are sort of frozen in this Fermi sea. They don't contribute to the physical behavior of your system. It's only those quasi-particles that can move around at the Fermi level. And they're called quasi-particles because they can disappear. I mean, particles fall back into a hole, and then both of them are gone. So they're not conserved as usual particles are. But there's nothing wrong with developing a theory of quasi-particles. So this, I think, gives you a first step of trying to understand how a Boltzmann equation can become relevant here. It's a very condensed system at a very low temperature, but the only degrees of freedom which matter to the behavior of the system are these quasi-particles. And so we can consider a very condensed system as a very dilute gas of quasi-particles. So in the case of fermions, this is called the normal Fermi gas. And that's what we are considering. Now, of course, I haven't introduced any interaction between particles yet. And if that is the case, then these quasi-particles also don't interact, and that would still be very uninteresting. So you have to also introduce an interaction. And this had been done by Landau, and he employed the adiabatic theorem of Ehrenfest to show that if the interaction can be very slowly or adiabatically turned on, you can choose a variable lambda, and you write a free Hamiltonian, and add this interaction term between the particles. Then the energy levels themselves, the structure of the energy levels doesn't change, although the values of the energy levels do change. But since the structure of the levels doesn't change, it still will be a system with a Fermi sea and a few quasi-particles hovering above them. And now the quasi-particles can also interact. And we can consider a quantum description of that gas of quasi-particles. And since, as I said, they're not necessarily conserved, we have to use the creation and annihilation operators that are familiar from quantum field theory, although in this case it's not a relativistic theory. But we can use the ordinary approach where we have creation and annihilation operators. They use the ordinary commutation or anti-commutation rules, and we have a number operator for the number of these quasi-particles with a given momentum. Now, we also assume that the interaction has a simple form. It is a pair-like interaction, which, as you can see, it takes away, it annihilates two particles with momenta K1 and K2, and then creates particles with K3 and K4. So the number of particles is conserved under this type of interaction. And that is the closest thing I can think of that resembles a classical collision between particles. So now we have a pretty decent analogy to the classical Boltzmannian. And I have to move briefly here, but I'm following an approach by David Snoke and also early work of him, which shows that you can derive an equation for the number of particles with momentum k and see how that changes in the course of time. And I won't go into detail about all of these difficult summations here. And these are terms connected to the interaction energies. This is an expression of the conservation of energy. And then there is this complicated operator of which you have to take the expectation of. And now, just like in the classical case, we need an additional assumption to transform this into an autonomous equation. And the way to do that, once again, is a factorization assumption. So what Snoke actually invokes a different assumption, but it's a stronger one that implies a factorization condition. And that factorization condition is simply that the expectation here of this sum of products of number operators is actually equal to a product of the expectations of all these number operators. So this expectation of a sum of products becomes a sum of the expectations, sum of the product of the expectations. And now once again, I have the change of the expectation of the number operators in terms of expectations of the number operators. It's now a integral with 4 terms instead of 2, but it's similar to the classical Boltzmann equation, and this is what is called the quantum Boltzmann equation. And just like before, we can formulate an H theorem. If this equation holds, you can prove that there is a quantity that can only change in monotonically in one direction. It's slightly different from Boltzmann's H function. It's called the semi-classical H function. Don't ask me why, but it doesn't matter. At least there is a theorem like this, which is time asymmetric and therefore codifies irreversible behavior. So the conclusion seems obvious. We have derived irreversible behavior in general for these system of quasi-particles. They tend to move towards thermal equilibrium. And we did that starting out from a theory that was time reversal invariant. And what was responsible for that result? It happened to be this factorization. But once again, if you ask yourself, is that factorization condition, does that favor or distinguish between the two directions of time? No, it's simply a factorization condition. It tells you that product of the expectation of the product of number operators is the product of their expectations. If you reverse time, that will still be the case. It doesn't single out one particular direction of time. So we have to ask the same problem. If the only ingredient you've added to the derivation is an ingredient which is symmetric under time reversal, you cannot obtain a time non-reversal, non-invariant result. And indeed, if you were to consider the situation at earlier times, you do get an anti-Boltzmann equation and an anti-quantum H theorem again. So again, the derivation of irreversibility here seems to be somewhat illusory. It is only there if you focus on positive times, but the opposite result holds for negative times. Now, there is a funny thing that distinguishes between the two situations, because in Boltzmann's case, for classical gas, you could at least say, oh, there is a way out of this whole conundrum. Let's go back to Boltzmann's own formulation of the Stokes-Thal ansatz and say, we're going to impose the factorization only for the initial momenta of a collision. In this case, such a way out is not possible because what we have here is the initial momenta, which are K1 and K2, and the outgoing momenta are K3 and K4, and we need factorization for all four of those. So we cannot, there's simply not an analogy to Boltzmann's Stokes-Thal ansatz to restore, if you like, the time reversal non-invariant aspect of the Boltzmann. So in this respect, the problem has only gotten worse than it was in the classical case. And I think that's quite remarkable because the hope was very often for authors that if you have a classical theory and you have a problem there in the foundations of statistical physics, let's go over to a quantum version of that same problem, and maybe our problem will disappear because quantum theory is better than classical theory. In this present situation, the conclusion is reversed. the problems only get worse if you go from a classical to a quantum theory. Now, I should also say we've been also looking, Snook's book is perhaps not the best place to start. It's certainly the most recent discussion of the quantum Boltzmann equation. But Snook is an experimentalist, and so his approach is not necessarily very mathematically solid. And we're also looking at other approaches for quantum Boltzmann equation. And I must say that those are in many respects much more mathematically sophisticated. But in the interest of time, I will skip any mention of that. I think I've been talking too long already. So let me stop here and open the floor for discussions. Thanks for listening.
Thank you. This is really interesting. And I have to confess, I haven't really thought about this. I wonder, the one point I really worry about this is like on the slide where you say we need to factorize 4 factors. And the reason I'm a little worried about that is I think about the classical case.
Yeah.
I think it's easy to, as Huang and other people do, just impose a factorization condition which is too strong, and then not really pay attention that you don't need the factorization condition as stated, but only factorization condition for the incoming momenta. I just wonder with like a little bit more care whether in fact you could get the quantum Boltzmann equation with imposing factorization for incoming and not outgoing momentum. That's sort of a question. That's a question. Yeah.
I don't know. I haven't seen any approach. But I can say I've seen one approach in which is sort of distinguished from all the other approaches I've seen. And that's from a paper by Van Weert and de Boer from 1978, who pushed the initial, the assumption about the initial state way past to the infinite past. And then, of course, you can't ask anymore what happened earlier. So if you, in that case, you sort of resolve the problem. And of course, in that case, your assumption is, you restore that this assumption breaks time reversal invariance. Because if you would reverse time, you would now have to make that assumption about the infinite future. So that is the only approach I've seen so far in which you explicitly use an assumption that breaks time reversal invariance. But it doesn't do that by distinguishing between incoming and outgoing momenta. Well, in the sense, if you say that in the incoming state, any momentum at that moment in time is incoming.
But if that's going to work, imposing some condition on the past state, and you're going to get an equation that's valid for future times, it has to be the case that imposing that past condition has implications for conditions at later times, which you could sort of impose independently at those times.
Which you could impose?
You could impose independently at those times. You could say, okay, I mean, here's the way I'm thinking about it. If I impose, say, think about the classical one. If I put
a little bit further.
If I impose in the classical case, if I impose some factorization at some initial time and go forward, if the Boltzmann equation is going to hold at future times, and at least for a while, you're going to have something at least approximates factorization for incoming momentum at the later time as a consequence of the condition I imposed at my initial time. In this case, you're going to have something similar. If you're taking a time in the infinitely far past and imposing a factorization condition yields a
Boltzmann equation valid for later times, then that factorization condition at infinite past is going to have implications. There's going to be something that's true at those later times. And I suggest that that's probably something like of the flavor of factorization of incoming momentum at other times.
Yeah. Well, I also have to assume that their version of factorization is considerably stronger than what we've been discussing so far. It's known technically as quasi-free.
Yeah, thank you. No, it's a very dumb question. I was confused at some point about the strict differences between the stalls, halts, and the factorization condition. I think I see it more now. But does it the stalls, halts, sats entails the factorization condition?
No,
Not at all. The other way around. So the factorization condition entails
the
this.
factorization condition entails the social concept. But well, no, I mean, I couldn't say that. The point is that it's probably easier if you, instead of distributions, you talk about probabilities. But the relative number of momenta amongst all the particles is different from the relative numbers of the momenta amongst the subclass of particles that are about to collide. That class is a subset of all the pairs, but the relative numbers in that subset need not be the same as in the entire set of molecules in the gas, the set of pairs of molecules. Okay.
Thank you.
So if the number of millionaires over the United States is some proportion of the population, it doesn't follow that the number of the citizens of New York, or let's say Manhattan, they have the same relative distribution as over the whole nation. Huh?
Even New York.
Yeah, okay.
I mean, the thing I was going to say mostly came up in the exchange with Wayne. I mean, my understanding of these conditions is you're normally thinking about imposing them either at the finite time in which the system is created or detached from whatever system it's capital to, or asymptotically in the past. That's how I understood a lot of these things. I actually just wanted to ask you something about the way you talked about the factorization condition in the classical case. If you wouldn't mind bringing the slide back. And this is partly perhaps me not understanding what Huang's saying. Yeah, that one there. So, I mean, obviously, as you've stressed, that the Boltzmann equation, as Boltzmann formulated, is talking about a slightly difficult to interpret, but in any case, non-probabilistic distribution function. I take it, if you want to understand this molecular chaos assumption, we need at this point to be probabilistic. As in, I'm not sure I'd understand how I can understand that as a correlation claim that as probabilities, there's no correlation between there's no 2-point correlation. Is that right? Do we need to be probabilistic to understand molecular chaos as formulated here, or do you take it as having a non-probabilistic formulation in the same way as Stossel ansatz?
In Boltzmann's, if you want to follow Boltzmann's approach in the most literal form, as Boltzmann gives it himself, then you're just talking about as an approximate characterization of the actual number of particles in the gas. So it's a relative frequency.
But okay, so then I don't know how to read it. I mean, what do I mean by why isn't it analytic then? I mean, the number of pairs of molecules with properties P1 and P2 looks like definitionally it's the product of the number of molecules with property P1 and the number of molecules with property P2.
So in a particular,
Yeah, sure.
In each,
in a particular spatial volume.
Yeah, sure. Yeah, it's
Not analytic, because there tend to be like correlations between here the momentum nearby things, and that could be false.
I'm not seeing how that can be true. I mean, if I'd possibly just missing something elementary. If I think about the number of pairs of people in this room, such that one of them has a red hat and one of them has a blue hat, that's definitionally going to be the product of the number of people in this room with a red hat times the number of people in this room with a blue hat, assuming they're distinct.
no, but
Or the left-hand side of the room. I mean,
but let me put.
Yeah.
Boltzmann gives some examples in what he means
Yeah.
by molecular chaos, and what he sort of says. What you have to exclude are situations in which each slow molecule is surrounded by very fast molecules.
yeah, so I understand how to read Boltzmann's version. I just don't understand how to read that version as a non-probabilistic.
But if you can imagine such a situation, then the number of pairs of particles, well, in the same volume,
Yeah.
in the small volume, might be different from your definition of the number of pairs
Well,
overall.
what is the definition of the number of pairs then? I've got a volume. What do I mean by the number of pairs in that volume with such that the first one has property 1, the second has property 2?
P1 and P1 and P2 are number of molecules in with P1, number of molecules in P2, but not restriction to a spatial volume, like in the gas as a whole.
Yeah.
And what this is saying is, if I look at a restricted volume and talk about number of pairs of molecules of P1 and P2 in that volume, that is the product of the proportions in without the restriction volume. So
Yeah, I'm really not seeing how to make. Perhaps I don't want to hold things up long. I'm really skeptical of how that can work. I mean, again, these things are non-probabilistic. They need to be smeared over a region such that there's a large number of particles. Ex hypothesis, these are spatially, and we're assuming a spatially homogeneous distribution. If we want to be spatially inhomogeneous, we'll need to put that in explicitly.
I should perhaps have said that Boltzmann starts out by assuming spatial homogeneity.
Yeah.
He has a very long paper, and in later paragraphs he removes that restriction and also talks about inhomogeneous gases. And then you get a more complicated Boltzmann equation with also a streaming term.
Sure, but let me add that in the framework. It's still going to be the case that I'm going to have a distribution which depends on positions and momenta. It's still going to be smeared over regions large compared to the interparticle separation for these functions to be well behaved. And then again, look at one of those regions. Fix a region. Yeah. In that region, the number of pairs such that the first one has property P1 and the second has property P2 must be the product of the number in the region with property P1 and the number in the region with property P2.
That's right, but it doesn't have to be the same number for all regions.
No, but again, block spatial homogeneity, and that equation will have to be indexed with the region on both sides in order to do the work it needs.
Yeah.
And then again, just pick one of those regions.
Well,
at the moment it's not indexed by region on either side. I'm trying to go with the generalization that Jos is talking about.
In the verbalization, but in a spatial volume,
yeah,
the number of pairs with respect to momentum between the three-dimensional space is proportional to,
Yeah.
and then on the thing it's proportional to is not in that quadrant. Is the product of product of in the gas as a whole.
Okay, well, I mean, look, just as a piece of text, that seems an odd reading of what's said there, but we could go to see what Yang says. I mean, the quantifier looks to me like it's on the front. I don't hold the discussion anymore. I'm really skeptical that this is a legit reading. of what's going on,
It's
so
a
we should
very
take it
good
offline.
question.
Use this opportunity to transition to insert myself. Yeah, so I have a different question. Maybe it's about the scope of the quantum Boltzmann equation versus the classical one, right? So in the classical one, I guess on top, it seems, well, at least back then, it seems to me maybe it would have been obviously fundamental that, like, you know, these are, or could be possibly fundamental, that these are particle ontologies, and then acting mechanically according to fundamental laws of physics, and then you derive this kind of irreversibility, right? In the quantum case, I guess it seems clearly non-fundamental, and so clearly somewhat unclear how this would generalize to be, I guess, metaphysically, well,
Yeah,
worrying issues. So I was wondering what this analogy here you think in your view is.
oh, yes, I would say that in both cases, well, it might be that these assumptions are fundamental in a sense, but the systems we are considering, the type of gases, both classically and quantum mechanically, are very, very special. So in the classical case, we have to consider a very dilute gas. I mean, in fact, if you want to make Boltzmann's equation precise, you have to go to a limit, the Boltzmann-Grad limit, in which the density of the gas goes to 0. So Boltzmann equation, in spite of its fame and in spite of its fame, is really only relevant to to extremely dilute gases, and has very little relevance to real gases that people work with in laboratories. So it's an extremely special situation.
Yeah.
But the interest this all work has caused over time is that this is at least it's the first, and perhaps it's the first example where people have tried to say, look, I've got a fundamentally time reversal theory, and yet I can derive from that theory the appearance of irreversible behavior. Whereas, of course, ordinarily people have said these two things are contradictory. Poincaré was famously opposed to the idea that you could have a mechanical understanding of nature, because he thought that the irreversible behavior of thermodynamics would make that impossible. So I think this is common to both. I mean, in the quantum case, it's also true. I mean, we have to exclude situations like superconductivity or Bose-Einstein condensation. In all those cases, the Boltzmann equation, quantum Boltzmann equation, is simply not applicable. So these are characterizations of very special systems, and it's not something that holds as a fundamental theory, a fundamental equation that governs all of nature.
Yeah, I just wanted to ask more about what you meant about the Boltzmann equation not being applicable to real gases. I mean,
well, I mean, real gases are not infinitely dilute.
no, but that just seems to suggest it's a problem with saying that that's how we should understand the Boltzmann equation. I mean,
that's a problem for
yeah.
the Boltzmann.
No, I mean, it's a problem for saying the Boltzmann equation can only be understood in the Boltzmann-Grad limit. I mean, let's not do that, and let's recognize there's some epsilons dotted around. I mean, let's just check that the number of 3-body collisions is extremely low compared to the number of 2-body collisions, which would be easy to check for. I'm pretty certain it's true for the air.
I'm not quite following you. There have, of course, been there has been a lot of interest in trying to generalize the Boltzmann equation to further equations that would be applicable to denser gases, and that would include also triples of particles colliding and so on.
Right, but in the air in this room, I need to check, but I'm pretty sure it's just back in the envelope. 3-body collisions are very rare compared to 2-body collisions. So the air in this room does look like the sort of system the Boltzmann equation is fine for. I mean, not exact, sure, but nothing's exact.
Well,
I'm just trying to understand what you meant by the gas.
there's this consideration about the density. There's also the consideration that real gases are not hard spheres.
Oh no, sure, but change the scattering term, but that's always. I mean, I guess it depends on the Boltzmann equation. Boltzmann equation normally you just say, okay, the scattering term is just whatever the 2-body physics gives you. I mean, sure. If what you mean is that the hard sphere version of the Boltzmann equation is applicable to the air in this room, then sure, I agree.
Yeah, I think this is a more or less a question of words. What we call the Boltzmann equation and what we don't.
Yeah, I guess. Okay, so I guess my point would be, I mean, insofar as the Boltzmann equation is inapplicable to the air in this room, I don't think the reason is because the air in the room is insufficiently dilute. It's because the scattering cross sections for air molecules aren't well modeled by the hard sphere model. But if you replace them with a better scattering thing, I think it works fine for the air in this room.
Well, I think we.
And then
Yeah, maybe it's a follow-up, maybe not, but so first you were considering the Boltzmann equation for diluted gases, and then when you moved to the quantum regime, you were considering the quantum Boltzmann equation for condensed matter systems. I wonder whether there is something that might be specific to condensed matter physics in the results that you get.
That there is something specific
to the condensed matter systems when you move to the quantum regime, because you seem to change the domain a little bit. So I'm wondering whether you will obtain the same results if you consider other types of systems.
Oh, I don't.
Something like
I don't
gases,
exclude that at all. This is just a matter of fact that if I look for papers or books that discuss a quantum Boltzmann equation, invariably what you get is work performed in condensed matter physics. That's simply a region or a regime in physics where such an equation does useful work in describing systems. There might be other situations, but I just happen to have not found much papers that are written about that. So I'm not claiming that there is anything special about condensed matter, but purely the simple happenstance that this is an area where people have discussed and applied a quantum Boltzmann equation quite extensively. And so that's why I'm looking at this area. But I see no reason why it couldn't also be relevant in other areas in quantum physics.
Yeah, interesting. And maybe I had a second question, just clarificatory question. So I do wonder what this semi-classical H theorem means. So why is it semi-classical?
As I said, I have no idea, but there is a whole bunch of variations, just like there are a whole bunch of variations of entropy. There are also a whole bunch of different definitions you could use for a generalization of Boltzmann's H. And so they all have particular names. There's a diagonal H, there's this, and so every one of them has a different name, and this one happens to be called semi-classical. And I personally have no idea why it's called semi-classical. I'm just reporting that that's a name people use. But I don't mean to intend anything more than that. It's just a name.